Welcome back to another video. Here, we will talk about t-confidence interval on a single sample. We have already discussed how to construct a confidence interval for the population mean when the variance is known. But what happens when the variance is unknown? In this case, we want to study the population mean, but we lack information about the population variance. From our discussion on point estimators, we know that the best approach is to replace the population standard deviation, sigma, with a sample standard deviation, s, in the normal statistic. This raises the question, can we still claim that x bar minus mu divided by s over square root of n follows a standard normal distribution? To answer this, we need to determine the distribution of this new statistic. Assuming that we have a normal random sample of size n, we previously introduced one normal and one chi-squared statistic. We explained that x bar minus mu divided by sigma over square root of n follows a standard normal distribution, and n minus 1 multiplied by s squared divided by sigma squared follows a chi-squared distribution with n minus 1 degrees of freedom. We have also introduced t-distribution and its properties and explained that t-distribution is symmetric and bell-shaped, like the normal distribution, but has heavier tails, meaning that it is more prone to producing values that fall far from its mean. Now, we will discuss how we can derive a t-statistic that follows a t-distribution with n minus 1 degrees of freedom. In order to derive such statistics, we need to divide a standard normal random variable with the square root of a chi-square random variable divided by its degree of freedom. Let's use the normal statistics in the numerator and the chi-squared statistics in the denominator. We can see that the n minus 1's cancel each other out in the denominator. We can also remove the square root and simplify the denominator to s over sigma. Next, we can cross out the sigmas in the numerator and denominator. This simplifies the ratio to x bar minus mu over s, divided by the square root of n, the statistic that we were looking to find its distribution. Going back to our question on whether can we estimate x bar minus mu divided by south over square root of n using a standard normal distribution. The answer to this question is we can, but only for large sample sizes. The reason is due to the properties of t-distributions. We just derived that x bar minus mu divided by south over square root of n follows a t-distribution with n minus 1 degrees of freedom where n represent the sample size. Looking at the bottom left figure, we can see that as degrees of freedom of t-distributions increase, its behavior becomes more and more similar to a standard normal distribution. You may ask, what about small sample sizes? For small sample sizes, we have no other choice but to use t-distributions, as the behavior of t and standard normal distributions are significantly different when the sample sizes are small. So, although it shouldn't be a problem to use standard normal distribution to estimate the behavior of this statistic for large sample sizes, it is more accurate to directly use t-distributions instead of relying on standard normal distributions even for large sample sizes. Now, let's see how we can construct a confidence interval around the population mean when both population mean and variance are unknown. Suppose we have a normal random sample of size n x1 to xn. We want to find lower and upper bounds so that the probability of mu being between these bounds is 1 minus alpha. To construct this confidence interval, we will rely on the t-statistic we just derived that follows a t-distribution with n minus 1 degrees of freedom. To build the confidence interval, we will push half alphas to each tail of this distribution. Given that the area under any probability density function is equal to 1, the red area in middle of the PDF should be equal to 1 minus alpha. The corresponding t-values should be t of half alpha with n minus 1 degrees of freedom and t of 1 minus half alpha with n minus 1 degrees of freedom. Taking advantage of symmetry of t-distribution, we can replace that t of half alpha with the negative value of t of 1 minus half alpha. Now, we can claim that the probability of any t-random variable with n minus 1 degrees of freedom being between negative and positive values of t of 1 minus alpha over 2 with n minus 1 degrees of freedom is equal to 1 minus alpha. To get the bounds around the population mean instead of a random t variable, we can replace t with our statistic of interest x bar minus mu divided by s over square root of n. Next, we multiply all sides with s over squared root of n to remove the denominator, subtract x bar, and multiply all sides by a -1. Doing these actions helps us to define the lower and upper bounds around the population mean. Let's go over an example together. Students have participated in a survey regarding their height, and we have access to the sample data. We are asked to find a two-sided 95% confidence interval on the average height of the students. First, we need to identify the population parameter of interest, which is population mean, as the question is asking us to construct the confidence interval on the average height of the students. Second, we need to confirm whether we know the population variance, and the answer is no, because the question is giving us no information on that. Now, we know that we need to construct a two-sided t-confidence interval around the population mean, using a single sample. We can do this either by hand or use Python functions available on Canvas. If we want to find the interval by hand, we need to find the sample mean first. We need to add up all the reported heights and divide them by 30 to find the x-bar, which is 174.27. To find the sample variance, we need to find the squared difference of each observation and sample mean, sum them up and divide it with 29, which gives us 265.3, or a sample standard deviation of 16.29. The requested confidence level is 95%, so we need to find t-value of 0.975 with 29 degrees of freedom, which is 2.045. Plugging in these values, we can construct a confidence interval around the population mean mu from 168.18 to 180.35. Alternatively, we can use confidence interval t function in Python to get the same confidence interval. Now, let's compare our t and normal confidence intervals we constructed around the population mean using the same sample under different assumptions about the population variance. We can see that the t confidence interval is much wider, but can you tell why? Please pause the video and take a moment to reflect on this. The main reason for switching from a normal confidence interval to a T1 is not knowing the population variance. Would you agree that by knowing less about the situation, we need to handle more uncertainty? If that's so, it should make sense that intuitively we are widening up of confidence interval because we have access to less information. From a statistical point of view, remember that t and normal statistics both follow probability distributions, and the area under their curves should be equal to 1. Although we pushed half alphas to both tails of this distributions, the t-values will be larger than z-values given that t-distributions have heavier tails. Also, please note although a sample size of 30 is relatively large, the t and normal confidence intervals much different. So please, try to identify the cases correctly. Instead of having two-sided confidence intervals, we can also define one-sided ones. This means that there are cases where we want to bound the population mean only on one side. The only thing different in our approach is that instead of pushing half alpha in each tail, we would push the whole alpha in a single tail. That is how we can get two one-sided confidence intervals. One from -infinity to x bar plus t-value of 1 minus alpha with n minus 1 degrees of freedom times south over square root of n. And another from x bar minus t-value of 1 minus alpha with n minus 1 degrees of freedom times south over square root of n to positive infinity. Thank you for listening to this short lecture on t-confidence intervals on a single sample.